Okay, welcome to lecture here. We're going to actually start lecturing today on chapter 12. Again, a reminder that these notes can be found up there on our Canvas site. So if you want the kind of copy of the notes, you can. And again, please put here in the chat box. And again, we'll just use that for roll. So every time we kind of have a meeting, either lab or lecture, just the first thing you do, just put here, and that'll take care of kind of the roll part of it. So again, like I said, if you need the notes there in the Canvas site, should have all the notes up there. And again, they have pretty much most filled in, except for some examples and stuff, obviously that we talk about, and whatever else I kind of scribble on the slide as we go through it. Get everybody in here. Okay, so we're going to start with chapter 12. And chapter 12 is about kinetics. So kinetics does deal with, as we'll talk about, sort of, how fast or slow a reaction basically will occur. So, there's kind of two big topics that we sometimes talk about in chemistry. And one of them you might have started to talk about a little bit last semester, which is thermodynamics. And thermodynamics, basically, a lot of times, especially what we'll see in this sort of class, is it looks to sort of answer the question of, will this reaction basically take place? Will this reaction be sort of spontaneous or non-spontaneous? And as we'll talk about in a later chapter, the idea of spontaneity doesn't necessarily mean what a lot of people sort of think, that if a reaction is spontaneous, then boom, it's going to occur like really fast and always occur super fast. It doesn't really mean that. And as we'll see later on in this sort of semester, what spontaneity means, or if a reaction is going to take place, it just simply means that under those conditions, a reaction will take place. Could be really fast, could be really slow, but under those kind of conditions, you would expect a reaction to take place. Some thermodynamic sort of values and stuff that you've probably seen over the last semester or so, I probably dealt more with energy and sort of that conservation of energy. So that law of conservation of energy, right? We don't lose energy along the way. We could transform it from one form to the next, but definitely don't sort of create it nor destroy it. And when we talk about energy, which is an important aspect of a lot of the stuff we talk about in this class, just a reminder that we're talking about things like perhaps enthalpy, which you might be familiar with. Enthalpy is kind of like the heat of a reaction. That is usually abbreviated with a delta H value, which means the change in the enthalpy. And just a reminder that if we do have a change in enthalpy and it is a negative value, that means that it is an exothermic process. Exothermic meaning obviously heat and energy is being released in that process. While if we have a delta H that's a positive value, that means that it is an endothermic process. Endothermic, again, meaning that heat and energy is being absorbed by the system here in this sort of process. So in terms of thermodynamics, that's probably, the main part of what you maybe have covered in Chem 50 and so forth. In I think chapter, I want to say 16 here, maybe 16 or 17, we'll talk more about some more thermodynamic sort of properties, things like entropy, things like Gibbs free energy, and sort of how that relates to it. But really in this chapter, what we're going to focus in on is kinetics. And kinetics actually is sort of the study of how fast a reaction takes place, how slow, I guess, as well, a reaction will take place. So kinetics really deals with the idea of sort of the rate and how fast or slow a reaction takes place. Again, when we talk about more thermodynamic type properties and things like that, we're talking about, just generally, usually, is that reaction under those conditions going to actually take place? So obviously, if we're talking about sort of how fast or slow a reaction would take place, one important aspect of what we talk about is the idea of reaction rate, or rate in general, right? Rate is basically the how fast you're doing something over a particular period of time. So usually when we're looking at a reaction, either our reactants or our products, we're looking at really the change in the concentration over time. Um, and that's why we have these sort of units here, which are molarity over seconds. So molarity obviously is a concentration, right? And we talked about it, I think, the other day as well, but molarity again is moles per liter. And we're really looking in the case of this situation, how the concentration is sort of changing, over a period of time, which is again why we have the seconds involved here. So if we looked at a sort of generic little equation there, we could actually look at this equation where A goes to B, arrow kind of eight each side of that there. So A goes to B. That's kind of what that is. And in this particular case, when this reaction takes place, it is basically a one-way arrow, right? So when we talk about reactions and we talk about types of reactions, one important aspect of reactions is the arrows that we see, right? A one-way arrow basically means everything's going from reactants to products. Nobody's coming back in the other direction. And we sometimes will see, definitely in the next chapter and a lot of chapters after that, is more what are referred to as reversible reactions, where we do have obviously the reaction has the potential to head really in sort of both directions here. So in this particular case, we have sort of a one-way street. It is definitely heading down to the product side here, which means if we sort of think about, what is happening, with time and how this reaction is proceeding, we would understand that, in order for us to make the products in this side, which is our B, we would have to use up some of our A. So probably if we were looking at something like time and time 0 and on, and we looked at sort of the concentration of A or B, we would see that probably at time 0, we have a lot of A there. And probably at time 0, we have pretty much none of the products. So as we sort of make our products, we have to use up our reactants. So we see a sort of downward direction while we see a gradual sort of increase happening, obviously, in our product side as we sort of make them. And we do sort of see that occurring here. By the way, again, concentration is what that bracket means. And again, usually what that means is molarity. So that's usually what that means when we look at something that has those brackets around it. So we could write something which is sometimes referred to as the rate expression to basically describe what is happening in this reaction. And that's what we see down here. The rate is equal to, in the case of A, minus, so there is a minus there, make it bigger, the change in the concentration of A over the change in time. So again, that's the change in the concentration of A over the change in time. While we look at the product side here, we could write a similar rate expression for it, where the rate is equal to the change in the concentration of B over the change in time. Now, there is a difference between these two, and the difference is right there. One is negative and one is positive. And the idea is what we were just talking about. Essentially, when this reaction takes place, we would expect our reactant, in this case, to start to decrease with this concentration. Again, we need to use our reactants to make our products. So the amount of reactants need to come down. At the same time, the amount of products will start to come up. So to represent that the reactants are basically decreasing with time, we put that negative number there, while with our products there, which is increasing with time, we have a positive value there. And really the reason for that is when we do something, say, like calculate the rate for a reaction. So when we calculate something like the rate, it should usually be a positive number. So when we calculate the rate, usually what we're looking for is sort of a positive number. So why is that negative really there? Well, if we just kind of make up some numbers here, grab something here, there you go. And if we just say, let's just say that we started with, in terms of A, the concentration of it. Let's say we started with 4 molar and ended with, say, 2 molar, right? And, or actually, let's say we started with, 4 and then ended with 2. In the case of A, we would do the rate is equal to minus, when we do the change in the concentration of A, the change in the concentration of A is essentially the final concentration minus the initial concentration. So in this case, what we would have for A would be 2 minus 4 molar divided by, we'll just say this was in 10 seconds or whatever, we'll divide it by 10. But the important part is when I take that, obviously 2 minus 4, what that's going to give me is a minus 2. And that minus that I get here, along with the minus that we have here, is going to turn our rate into a positive number of 0.2 molarity per second. So that negative there is really important because what we know is as the reactants are decreasing with time, the final concentration of our reactant is always going to be a smaller number than what we started with, right? Because it should be decreasing. And that extra negative that's put in there for our reactants will always make sure that our rate turns out to be a positive rate, which is ultimately what we're looking for. Again, if we looked at something like B, you know, how if we had made up some numbers here for B in that same sort of 10 seconds, you know, obviously B would start at 0 molar and maybe end at, say, 2 molar, right, as well. So when we did it for B, the rate would equal the change in the concentration of B, which means final was 2, initial was 0, divided by our 10, going to yield us, again, our positive rate in this particular case. So that negative there on the reactants is important because technically when you do that subtraction of your final minus initial, you will end up with a negative number for your reactants. And again, that negative basically implies that we are decreasing that concentration over that period of time, while the products are gaining it, and it should be increasing with that period of time. Any questions on that there? Again, if you do have questions, feel free to ask. You could ask again through your microphone if you like, or you could chat me a question if you want to do it that way as well. All right. So looking at a reaction such as this, again, as I sort of drew there, you know, if we look at what's happening here, A is sort of the black circles and B is the red circles. So again, at time 0 here, before sort of the reaction starts, we can see we pretty much have mostly A's. But as this reaction is progressing with time, we do start to see a disappearance of those A circles. We start to see a lot more of those red product circles start to develop. And we end up with, at the end of the time there, a much increase in the red, which would be our products, right? Starting at 0, sort of increasing, while our reactants that we started with started higher in terms of amounts and obviously started to decrease. Again, with the idea that it pretty much needs to use up those reactants to make the products. So again, we see that decrease in time, or decrease in concentration over time, which is very, very common. So how in sort of a lab or something like that, you know, could we sort of monitor, you know, the change in the concentration, you know, in a reaction? So there's a number of different ways that you could kind of monitor what's happening in a reaction, and see, you know, and follow it over a period of time. So one common way that we could kind of do that is through the use of, are taking advantage of solutions that do make some type of color. So if we have some type of solution that is sort of has a particular color, we could actually follow the change in color and really relate it back to concentration. So for example, here, if we look at this reaction, you know, Br2 is like this guy over here. So Br2 does have this sort of color. So starting out, we have this dark orangey type color. And as the reaction proceeds to the product side, these guys on this side is more colorless, obviously. And we start to see a decrease as the time goes on in terms of the color. So we could take advantage of that by doing something like, perhaps you maybe have used it before, like a spec 20 or a spectrophotometry, where basically we set it up in such a way that we have a light source. It shoots light at a specific wavelength, depending on sort of the color you see. It goes through the sample, and it really does measure one of two things. It will then go to the detector on the back end there. Sometimes we measure absorbance, or sometimes we measure what is sometimes referred to as percent transmittance. And absorbance is usually most of the time what we measure. And what we're measuring there basically is kind of like the name implies, it's the amount of light that basically gets absorbed by the solution. And the absorbance of that light is related to the actual color of the solution. So sort of the darker the solution, the more light's going to be absorbed, I guess, absorbed. And the sort of lighter the solution, less light is going to be absorbed, because it's just going to go right on through with no problem. Percent transmittance is basically the ratio of light that goes in to the light that reaches the detector. That's really the percent transmittance. Now, if you've ever used something like a spec 20 before or something like that, you know, one thing that you do is you usually set the wavelength to a specific sort of wavelength. And how do you know where to sort of set it? A lot of times what you do in these sort of experiments is you basically take the absorpance of your solution at many different wavelengths. And you could kind of set up this curve, which is used to basically figure out where you should set the wavelength. By the way, wavelength is lambda, right? And just a reminder, C is equal to lambda times the frequency, right? Is probably an equation you might remember. And what we're looking for is actually where that solution absorbs the greatest, or the maximum absorbance that occurs. And why is that important? Well, we would want to set our sort of machine there to that wavelength, because when we run samples, what that allows us to do is really pick up absorbance values pretty much all the way underneath this curve, if you will. So what would happen if you decided, hey, I'm going to set mine up over here. I'm going to set the machine to the wavelength in this region. Well, what that means is you pretty much only have the ability to measure absorbance about that much, which means probably if you did that in this particular example, what you would find is most of your samples probably wouldn't give you a value. You get a lot of error messages and stuff like that. So it's important to know the proper wavelength to set a machine such as this to. Also confusing to people is sometimes they're like, well, my color here that I see, orangey red type color, you know, I definitely should, you know, in the visible part of the spectrum where we see colors, right? Roy G. Biv. I should definitely set the wavelength in the red color, right? That's definitely where, you know, I should set it. And actually that's incorrect as well. What we see in terms of color, when we look at a solution, what we see in terms of the color is actually the complementary color to the wavelength of light being absorbed. So although it appears to us to be this reddish color, for example, it's actually not absorbing light in the red region. It's absorbing light in the complementary color to red. So maybe out there in the greenish blue area is where you would actually set the wavelength if you were doing an absorbance value for this. So that's sometimes confusing to people. They're like, wait a sec, I just set the machine to a wavelength in this area, but the color I'm seeing is like over here. And again, that's the reason why, because what we actually see is the complementary color to the light being absorbed. So we actually would set the machine to a wavelength that's of the complementary color. And again, to really sort of narrow in on the exact wavelengths you should set it to, that's why you would kind of do this little experiment here, or part of this experiment here, to really figure out, what you should do. Any questions on that so far? Now, it's important how we actually turn these absorbance values into maybe concentrations and really following the concentrations. We use something which is referred to as Beer's law. And also you might remember Beer's law. Beer's law, a couple of different forms, but one form is A is equal to B times C. A is absorbance. C is concentration. And B is Beer's constant, which is usually made up of the path length and the molar absorptivity constant. So A is equal to BC. So there's a couple different ways, and one way you could do is sort of graphically, you could figure out what your Beer's constant is, and what that allows you to do is you could take your absorbance values that you would get in the experiments and solve for concentration, would be the absorbance divided by Beer's constant. So this is a way that we could follow the absorbance and then relate it to concentration by using this technique here. Any questions on that there? Obviously, we could turn this into sort of a relationship in terms of a rate by doing this, obviously, over a specific period of time. So we could do that over a specific period of time, and that will allow us really to see, again, over that period of time, how the concentration is changing. So we do say that the change in the concentration of Br2 in this case is proportional. That's what that little alpha symbol means. Proportional to the change in absorbance. So at the beginning of this sort of experiment here, we would expect pretty high values for absorbance. And as this reaction basically continues, we would have high values for absorbance. And over the period of time, we would expect the values to drop to very low values, to probably almost no absorbance happening there at the end. Again, with no color in that solution, it's not going to absorb any light, and we would get really no absorbance values. Any questions on that there? So it is kinetics. So a lot of things that we do see in kinetics is a lot of graphs, there's a lot of tables that we very often will see. And again, there's a couple of different sort of rates that we sometimes will talk about. But basically, if we wanted to figure out, for example, here, this is a graph following the change in really the concentration of Br2 over time. And we do see what we would expect. Again, Br2 is a reactant, so we should expect a decrease in its concentration as a period of time. You can figure out the instantaneous rate, which is basically the rate for a specific period of time, like what we see here. We do see, this kind of window of time, sort of the rate. You could do that by taking the tangent of the line there. That's what all that is there, the slope of the tangent, to sort of do that. We also have an average rate, which is basically the change in the concentration of Br2 over the change in time. Again, we do see what we talked about earlier. We have the negative sign here because it is a reactant. And that's again because when we do the final minus the initial for our reactant, overall, we are going to get that negative number, negative and negative, again, going to turn our rate into a positive number, which is what it should be. Now, if we just look at the units, again here, on top is molarity, on bottom is seconds. Nothing's canceling out, so our average rate here would be molarity per seconds. So what is sort of the difference between maybe an average rate and sort of an instantaneous rate? So you could kind of think of it like, when you're driving, maybe you're driving here to wherever, Arizona or something like that. And, along the way, maybe you're doing, you did 70 along the way, maybe did 75 miles an hour along the way, maybe did 80, hopefully not 90 or 100 along the way. Maybe there's pockets of that, I suppose. And, for those instantaneous points in time where you're doing 80 or 90, you're instantaneously traveling obviously a lot faster. But if you maybe average your whole trip from beginning to end in terms of how fast you drove, maybe you only drove on an average of 70 miles per hour, but there were pockets of windows where you drove much faster, and there's pockets of windows where maybe you drove a lot slower. And on average, you ended up with sort of an average rate as to how fast you sort of drove in that particular case. So that's sort of the difference. Usually, a lot of times, what we look at is sort of the average rate of the overall sort of reaction over that period of time. But again, kind of like driving, if you just kind of take a snapshot of a period of time, you may actually be going faster than you did on average, or you may be going kind of slower as you did on average as well. So again, here's a representation again of some common type of tables that you might see in these kinetics sort of problems. And the information that we see here is we do see a couple of things. We see the time. We see basically how the concentration of BR2 is changing with time. And as we talked about before, we do see, kind of at time zero, we have a much larger concentration of BR2. And as we would expect, it starts to decrease with time. Again, the idea there is we got to use up our BR2 to make our products. And again, if we kind of instantaneously look at the rate, we got some different rates happening here. Maybe it's a little faster there at the beginning, then it kind of slows up here towards the end. But there is a relationship when we look at a certain sort of process here or property of this reaction that is relatively constant, and that is over here, and that is the little k. And if we sort of rearrange, the rate is equal to k times the concentration of Br2 and solve for k. K is what is known as the rate constant, sort of how fast or slow a reaction is proceeding. Now, that is lowercase k, and I'll draw it really small, not to be confused with what we'll talk about mainly for the rest of the semester. Maybe not that big of a drawing there, but capital K. Capital K is the equilibrium constant. And that is not what we're talking about here, but we're talking about little k there, which is the rate constant. And again, it deals with basically how fast or how slow a particular reaction is proceeding. This format here, we'll see a little bit later on as well and talk a little bit more about it, but this is what is sometimes considered a rate law. And a rate law basically has a rate constant. It has the concentration of our reactants that are happening here. And we can basically do a little rearranging here. And in this particular case, they can solve for the actual value by using a graph such as this here. We have the rate versus the concentration of Br2. And what we see is we get this number. The number is not really important, but let's talk about maybe how they got to those units. So how do they get to those units? Well, the rate is something like molarity per second, as we see up here. And it's going to be divided by the concentration of Br2, which is molarity. That means molarities will cancel, leaving us with 1/seconds or reciprocal seconds. And also, as we will learn in this chapter, the units that you see associated with the rate constant are really important. They actually do give you a good piece of information or a lot of information. When we look at this particular units that we see here, this is what is sometimes referred to as knowing it's a first order reaction, which we'll talk about what that is a little bit later on in this chapter. But something to keep in mind as we go through this kinetics chapter, it's really important not to just ignore sometimes the units that you are given, especially with rate constants. They oftentimes will give you a very big hint as to sort of what type of reaction you're dealing with. And as we'll see a little bit later on this chapter, that's really important because if it is a first order reaction, there's a whole set of formulas that you need to use rather than say if it was a second order reaction, which you would use a whole bunch of different formulas for that. So a lot of times in problems, as we'll talk about, they don't in sort of blinking lights go, hey, we're dealing with a first order reaction or anything like that. They just kind of give you the units of the rate constant, and they assume that you know sort of what it means. And again, we'll go more detail about that later on in this chapter as well. Any questions on any of that so far? Okay, so what happens though, if we do have perhaps a reaction where, maybe there's not a lot of color to sort of follow, maybe things are not 100% sort of able to be absorbed with light. So obviously, if we have some type of process where lots of things or most everything there is sort of colorless, we would not be able to use something like a spec 20 or spectrophotometry to do that, because we would have nothing that would be able to absorb light. You would get pretty much no absorbance values because everything's sort of colorless. So in a process where perhaps we are doing something where we're producing a gas, like in this one where we take some hydrogen peroxide and it basically will decompose into water and some O2 gas, we could actually use the ideal gas law here to help us out and sort of figure out what is happening in terms of the concentrations, especially of something like O2. Ideal gas law, as hopefully you remember, is that PV equals nRT. P is pressure, right? And out of all the gas laws, this guy has the most restrictions in terms of units, right? So P is pressure. It has to be in atmospheres when you use the ideal gas law. V is volume, which has to be in liters. N should be moles. T should be in Kelvin. And R is the gas constant. It is a value of 0.08206 liters times atmosphere, Kelvin times mole, or some people used a rounded version, 0.0821, which is perfectly fine. So if we take, say, the ideal gas law, for example, and we actually solve it for N divided by V, and if you did that and rearranged it and solved it for N divided by V, you divide V to the right-hand side, divide RT to the left-hand side, you would end up with P over RT. So why would that necessarily be important to do? Well, if we just look at what the units are for these two guys, N is moles, volume is liters, moles per liter, that is also what we call molarity, right? So as odd as it sounds, sometimes we don't associate like molarity with gases and stuff like that, or concentrations in the sense of molarity. We oftentimes think about it in terms of solutions. This is a way in this sort of experiment, as we see here, by just simply measuring the pressure over time, we could actually figure out how the concentration of something like oxygen is changing. It should be increasing, I would think, with time. And why we could do that is if you just simply look at our rearranging of our ideal gas law, the bottom guy is a constant, which means it's not changing. Probably if you're doing this experiment, probably you're not changing the temperature. It's being done in kind of the same room, which means really the only thing that's sort of changing and the only thing that you would need to monitor would be the pressure, which you could do with a setup such as this. You kind of monitor the pressure here. And by doing so, what you essentially be doing is figuring out, how the concentration here of our oxygen gas is changing with time. So since we're dealing with oxygen, we would expect it to kind of be different than some of the other things we talked about, because oxygen here is a product at time 0. We would expect not to have very much, if any, probably none. But as time continues, we would expect the difference is we should sort of see it start to increase, right? Because it is a product in this particular case. So using that sort of arrangement there and kind of what I wrote on there, we could take 1 over RT times P here. Get rid of that there. And we will get the rate is equal to the change in concentration of O2 over the change in time, which again basically just means, as we see here, 1 over RT delta P. So really, these are the only two things that you would have to monitor. And just by monitoring the pressure, and obviously since it has something to do with time, monitoring the time, we're able to really follow, in this case, how oxygen is changing as this reaction progresses. And again, this is a situation where really none of those guys have any type of color, so we wouldn't be able to use spectrophotometry and really following absorbance values here. So this is a nice way, obviously, as you can see, another sort of way that you could kind of do a kinetics experiment and follow what is going on. Any questions on that there? Here again is sort of that graphical representation of what we were just looking at. And again, you do see sort of what we would expect in this graph. Again, starting at time 0, pretty much no O2 present. Again, by monitoring the pressure, the only thing, just so everybody's clear, right? The only gas that's obviously in this reaction is the oxygen. So as soon as we start to see some pressure rising, it could only mean that the oxygen was being produced because there's no other gas there producing pressure. And that's why we can definitely relate it to the oxygen gas in this particular case. Again, you can take that slope of that tangent line if you want and get sort of an instantaneous rate. You can let it run over the whole period of time and, you know, kind of get the average rate that's happening in this particular reaction. So then let's talk about sort of reaction rates and stoichiometry and sort of what is happening here. Sorry about that. Some of these things got shifted a little bit. So this is 2A that goes to B. Just kind of cross that out. So when we look at this and when we take into account sort of reaction rates and how reactions are sort of progressing, we still need to look at everybody's favorite thing, which is stoichiometry. So we still need to make sure that even though we're talking about rates and how fast or slow reactions are happening, you know, how much product we're making, how much reactants we're sort of losing over a period of time, we do need to take the stoichiometry into account to make sure that we do have sort of the right ratio of what's happening here. I'm sure you remember, but again, just a reminder, stoichiometry is based off of the coefficients off the balanced equation. And since nothing's there, that's assumed to be a 1. And we could get a relationship here that for every 2 moles of A we throw in there, we get out 1 mole of B, right? So that is really our stoichiometric relationship here. And we can write 2 rate expressions for this reaction. We could write one where we have the rate is equal to, and again, that is minus there, minus, because A is a reactant, 1 over 2. So where does the 2 come from? Well, it is 1 over the coefficient. So the coefficient that we see in front of A is 2. So that is where that comes from. That is the coefficient. Times the change in the concentration of A over the change in time. When we get to our product side, we have the rate is equal to, again, as we talked about earlier, no negative because it should be increasing with time. So it's a positive number here. And there's actually no 1 over anything. There really is, but it's 1 over the coefficient. Coefficient is 1, which means it's a 1. So again, that's why we don't have necessarily anything written there, but technically it is 1 over 1 there. The change in the concentration of B over the change in time. So in general, if you want to write these rate expressions and sort of take our stoichiometry into account, and again, C to C, we have this general equation here. We would take 1 over, the rate is equal to minus 1 over the coefficient there of A, change in concentration A equals 1 over the coefficient there for B, also minus change in concentration B over change in time equals, now we're on our product side over here, 1 over C, the change in concentration C over time, and 1 over D, change in concentration D over time. This again is what is referred to as sort of the rate expression. This is usually sometimes referred to as the average rate. And this number here is usually a positive number when you do it. What does this mean? This means that pretty much if you know just one piece of information about anybody in that reaction, maybe you know how a reactant is changing over a period of time. Maybe you know how a product is gaining its concentration over a period of time. Maybe you just know the average rate. It will allow you to figure out how every single person in that reaction is changing over that period of time by doing this. You could set them all equal to each other. You could set them individually equal to the rate. It basically works the same. You know, you could pull out just the parts that you need. Yeah. So again, in terms of, and again, this is what is referred to as sort of a rate expression. And these negatives are always for just the reactants that do need to be included. Again, for what we sort of did a little bit earlier, because the reactants are decreasing with time, their initial concentrations are always going to be larger than their final concentrations, which means when you technically do this part of the calculation for, say, your reactants, this number is going to be negative. And with this extra negative up in front, that is going to turn that rate that you're technically calculating into a positive number. And that's different than our products, which should be increasing with a period of time. So because they're increasing with a period of time, when you do the change in the concentration of your products, you will technically get a positive number here. And that's why there's no negative, obviously, in front. Positive, positive, again, allows us to yield a positive rate when we calculate it. So you definitely want to make sure that you start with a balanced equation, because always the balanced equation would have the correct mole to mole relationship. And that's really what this 1 over the coefficient part is, 1 over that coefficient. That is sort of what that's doing for you, is taking the stoichiometry part of it and kind of doing it all together in one calculation. You could absolutely, and we'll see maybe an example of this a little bit later here, that you could absolutely kind of do a stoichiometry problem first and then kind of do the rate part of it or the kinetics part of it and do them separately, and just do a basic kind of, 2 moles of A to, 2 moles of A to 1 mole of B, and then get the moles of B, and then kind of put it into the kinetics information and the rate. So you do the stoichiometry part sort of separately as well. But sometimes people get confused as to sort of where to go at that point. So by doing this 1 over the coefficient, it essentially kind of incorporates both the stoichiometry part of the calculation with the kinetics part of the calculation kind of together. And it hopefully will obviously allow you to not forget to do the stoichiometry part of it. So that's sort of why, we see that 1 over the coefficient. It just kind of incorporates both of those parts sort of together in that calculation. So as I was saying before, because all these guys are really equal to each other, you can sort of mix and match and really pull out, what you might be interested in. So let's just say I was given information about A and I want to know something about C. So, I could do the problem individually and just go, hey, I know the rate is equal to -1 over A, the change in the concentration of A, over the change in time. I could also say I know from this that the rate is equal to 1 over C, change in concentration of C over the change in time. And if I was given enough information about A, what I ultimately a lot of times would be able to do is to get a number for the rate, right? Whatever that number may be. I'll just say it's a 50 molarity per second, just made it up. So if I'm able to do that because they gave me some information about A, that number that I get for the rate is the same number that would be here. So I would then know this guy would be 50 molarity per second, 1 over C, change in the concentration of C over the change in time. And, you know, I could then isolate this if that's what I'm looking for, multiply the C over. And again, by multiplying that guy over, that's going to do the stoichiometry part. And, you know, I'm able to do that. So, you know, you could kind of mix and match based on the information given, kind of pull everybody out and kind of individual sort of calculations of what you're looking for. And again, relate into each other because they are all basically equal to each other in that sense. All right, here, let's see. All right, so why don't you give this a go? All my arrows moved. Let's move that over there. Cross that guy out there. So why don't you write the rate expression for this guy and see what you come up with? Take a minute, and then we'll talk about it. Okay, so let's take a look and see how we're doing. So we want to write the rate expression. So again, since we don't really have numbers or anything like that, we could just write everything together. We could start with the rate here, which would be like the average rate. Again, looking at our CH4 coefficient is basically a 1 there, but it is a reactant, which means it is changing with time, so we would want the negative. Technically speaking, at this point, it would be 1 over 1, which obviously is 1, so we don't need to put the 1 here. The change in the concentration of CH4 over the change in time. That would equal our next one here, which is also a reactant, so it should be negative. The coefficient here is 2, so that would give us 1 over the coefficient. And again, that's going to take care of any type of stoichiometry problem part of the calculation. Change in the concentration of O2 over the change in time. We are now then moving to our product side, where again, we do have a coefficient of 1, which is basically going to end up the same as this guy. But because this is products and we would expect over the period of time it to start to increase, this would be a positive number on the back end here, change in the concentration of CO2 over the change in time. Again, coefficient there 1, which is why we have nothing there. And our last product here, again, going to be a positive here, does have a coefficient of 2, so that'll be 1 over 2. Change in the concentration of water over the change in time. So this would be the rate expression here for this reaction. And again, if you had actual numbers, you could really pull out any part of that and sort of figure out again how methane is changing over time, how oxygen is changing over time, how carbon dioxide and water is changing or really being produced over or formed over that same period of time. Any questions on writing the expression there? Okay, so why don't we actually try one then, maybe with some calculations here. So for a reaction given, the I changes from 1 molar to 0.865, I'm sorry, 0.868 molar in the first 10 seconds. Calculate the average rate in the first 10 seconds and how is the change in the concentration of H plus over the change in time? What is that going to be? So you should end up with 2 values. So why don't you take a couple minutes, try to work through it and see what you come up with. A lot of guys in here, but we definitely have information about I minus. And ultimately, we're interested in H plus, what's going on there. So even though there's a lot of other stuff involved in this sort of reaction, it's best obviously just to focus on the 2 things that obviously either we have information about or we're trying to find. So if we looked at I minus, again, we do see it is a reactant, and we could write a rate expression for it that the rate is equal to minus, again, because it's a reactant, 1 over 3 because of its coefficient, the change in the concentration of I minus over the change in time. We also could do a similar approach here for our H2, which we're interested in, and that would be the rate. H plus is also a reactant, so that would be minus there because it's a reactant. Coefficient is 2, so that'll be 1 over 2, change in the concentration of H plus over the change in time. Any questions on how I got those 2 things? Now, a couple of other pieces of information that's obviously given to us, which is relatively important here, is obviously we're given the starting concentration of I minus is 1 molar. We're also given the final concentration, in a sense, of I minus is it drops to 868. We also know it's going over 10 seconds. So, you know, the total time there is 10 seconds, but basically, right, we're assuming, or you could probably make a pretty safe assumption that the initial time there was 0 and probably the final time is 10 seconds. So, you know, you could kind of make that assumption probably safely here. So really, because we have information about I minus, that is where we want to start. And that's going to allow us to get to the rate here. So we really could just plug it right in. So the rate would equal -1/3. Again, the change in the concentration of I minus is going to be our final, which is the 0.868. Because it's a reactant, it's decreasing with time versus R1. And again, you could do your 10 minus 0 seconds, or really 10 seconds on the bottom is fine. And when you do that, what you will end up with is something like 0.0044 molarity per second. And again, this is going to be the rate. You can see it is a positive number, and that is because when we do this subtraction here, that's a negative number. We have that negative here. Again, these two guys are going to turn us into a positive number for the rate, which is what we expect it to be. Any question on that calculation? Now, why is figuring out that rate important? Well, this rate right here and this rate right here, they're the same, right? They're the same guy, the same thing. So by doing this calculation, we have now figured out the rate here, and that's going to allow us to relate this to the H plus concentration. So focusing in on our H plus concentration, or what we're looking for, again, our rate is equal to -1/2, the change in the concentration of H plus over the change in time. Ultimately here, what we are trying to find is really is this part right here. We're ultimately trying to find what is the change in the concentration of H plus over the change in time. Yeah, so the H plus is not the per se the same as the I minus, but the overall average rate for that reaction is the same. So it's actually the rate's the same. And that just goes back to, we could, if we wanted to, for this reaction, pretty much write a rate expression where the rate is equal to, you know, the change in the concentration of H2 over 2, change in time minus equals minus, like we have 1/3, change in the concentration of I minus over the change in time. I won't continue, but basically we could set them all equal to each other, which means when we break them out, each of those individual guys, the rate is the same for both of them. And it's basically the average rate for the overall reaction. Other questions on that? You're welcome. Any other questions? So again, that's why it's sort of very useful, this sort of rate expression. It allows you, you know, because they're all really related to each other through the average rate of the reaction, you can kind of pull each one out individually. And that's really the thing that sort of ties them together, or whatever the two you might be looking at, or three, or however many you're looking at. It's that overall sort of average rate for the reaction that sort of is that tying part to everybody that's here. So at this point, we are looking for what's in the box here. From the previous step, we calculated the 0.0044, which is our rate. So basically, if we put that in there, we got 0.0044 molar seconds is equal to -1/2. Again, the change in the concentration of H plus over the change in time, which is this part here. And this is the important part as well. To get the 2 to the other side, you need to multiply the 2, right, to the other side. So We would multiply the 2 to the other side, just like we would do it here. But the other important thing is there's also a negative, right? So technically -2 to both sides. Those are going to cancel out. And that's going to give us a negative 0.0088 molar seconds, which is how the change in the concentration of H plus is changing over time. So why is that negative important here? It's important because this is a reactant. And as we talked about, we would expect it to be decreasing with time. And that's why it's important to have this negative here, because that's indicating that our H plus is actually decreasing with time. Any questions on that calculation there? So again, by having that kind of 1 over the coefficient, it does sort of do all the stoichiometry part sort of easily for you. Again, you could have kind of tried to do a I minus to H plus mole to mole relationship first and then put it in. You could do that approach. Any questions on that? Okay. So why don't we try another one here and see what you come up with here. All right, so why don't you give this a go? We have 2.4 times 10 to the 2 grams of NOBR. The molar mass is 109.91. It decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. What is the average rate of BR2 production and in molarity per seconds, if that's our equation? So take a few minutes, see what you come up with, and then we'll talk about it. Hopefully we'll all end up at the same spot. So in this case, we are given the amount of NOBR, and it's decomposing in a basically 200 milliliter flask in 5 minutes. We want to find the average rate of production of BR2 in molarity per second. So couple of ones that we're interested in, obviously here, the NOBR. So we could write our rate expression for that guy, which is the rate is equal, again, it's going to be negative because that is a reactant, 1 over 2 change in the concentration of NOBR over the change in time. We're also interested, obviously, in our BR2 production. So that would get us a rate is equal to, again, because it's a product and it also has a 1 for the coefficient, BR2 over the change in time. So we'll focus in on, obviously, this guy here, since they were nice enough to give us that information. They didn't really give us molarity, but they did give us grams and the molar mass. That's enough to get to moles. And we do have the volume over here, which we could get into liters. So we do have enough information to really figure out the molarity of the NOBR. So that's what we probably would want to do first. We would take the 2.4 times 10 to the 2 grams of NOBR. We would use the molar mass, which was given to us, and this is obviously grams per mole when we do molar mass. So grams would go on the bottom, 109.91 grams per mole of the NOBR. The grams would cancel here, and we would end up with, I believe, 2.1836 moles. Close to molarity, but that's just moles. So over here we have 200, right? It's basically 200 milliliters, which is the same as 0.2 liters. So we would divide that by 0.2 liters, and that will give us our molarity, which is 10.918 molar. That technically would be what would go up there on top. I would also say it is probably negative 10.918. Any questions on that there? Why would I say it's negative? Well, that is a reactant, so we do know it is decreasing with time. And technically this number here was probably found by taking the final minus the initial. And as we talked about, that would give us a negative number. And that also will help us out here to turn that negative into a positive value in that particular case. Any questions on that part so far? At this point, we do need the change in time. So basically here we're running at 5 minutes, it looks like. So we could assume that's probably the final time. Initial time was probably 0, for example. So obviously a little conversion there between minutes and 60 seconds, perhaps. So that's going to give us 300 seconds. Again, the reason I'm turning that into seconds is because it wants it in seconds, right? So otherwise I would be in minutes if I left it in minutes. So at this point, we have everything we need to figure out the rate. So the rate would equal minus 1/2. Our change in the NOBR was found to be minus 10.918 molar. Our seconds was found to be 300 seconds. And that is going to get us 0.018 molar seconds as our rate, which would be that answer there. Any questions on that there? So that's just the average rate. We do then want to relate it to the BR2 in this case. So as we saw earlier there, that the rate is equal to the change in the concentration of BR2 over the change in time. We're essentially looking to solve for this. We already know the rate from here, which means that is also the answer for really how the BR2 is increasing with time. Again, here we do get a positive number of 0.018 molar seconds. Any questions on that there? Okay, so this is obviously one approach and kind of a good little approach here to do these type of problems, taking into stoichiometry with it. So as I mentioned earlier, you could, if you're more comfortable doing it, sort of approach it as a stoichiometry problem followed by sort of a rate problem. So if we were to sort of approach this problem in that fashion, kind of a stoichiometry followed by the rate part of it, we could actually pick up right about here, right here. So we could convert our grams into moles. So if we picked up with that, with the 2.1836 moles of NOBR, we could just use basic stoichiometry here. And this again is 2 moles of NOBR is equal to 1 mole of BR2. So we could do that part right here. Again, we got our 2 moles of NOBR and 1 mole of our BR2. That would get us 1.0918 moles of BR2. So we just kind of did the stoichiometry part to get us to the BR2. Dividing that by our volume will get us 5.459 molar. And at this point, now that you have the molarity of the BR2, you then could divide it by the total time. And you will end up with obviously the same answer here. So really, what are we doing here? Well, there's our half and there's our half. Yeah. So that's sort of where I was talking about earlier, that, we're really just kind of incorporating the stoichiometry into the rate sort of calculation. But again, you could, as you can see here, kind of do it separately if you wanted to, and you'll come out the same way. So, either way is fine, but maybe it's a little bit easier and straightforward to kind of incorporate it, the stoichiometry with the 1 over the coefficient, so you don't kind of mess it up. But that's essentially why we do the 1 over the coefficient. Again, that's taking care of the stoichiometry, as you can see there, and sort of the long way of doing the calculation if you want. Question on that? Okay. Question on rate expressions. Obviously, you need to be able to write rate expressions. You need to be able to obviously solve for problems such as this, figuring out how things are changing, average rates, and stuff like that. Okay, then let's talk about some factors that sort of affect the rate of a reaction. The nature of the reactants. So kind of the starting materials have a big play in sort of how fast or maybe how slow, if you want to think about it that way, a reaction might proceed. Small molecules typically do react faster than larger molecules. Gases will react faster than liquids. Again, if you just think about gases, they're flying around constantly. They have a lot of energy, so they're very reactive. Liquids not moving around as much, obviously, as gases. And then obviously solids are much slower than everything else. Solids are pretty much, packed in there pretty tight, not a lot of room for movement, so not a lot of energy sort of happening, so not very fast in terms of those reactions. When we talk about solids, if you have more of a powdered solid than a block solid, it's more reactive. Again, it just gives a lot more areas for reactions to begin, is because it's kind of spread out versus then everybody's kind of packed together in a tight one. There are certain chemicals that are more reactive than others. Perhaps you remember the activity series of metals. You probably talked about that again with more of a single replacement reactions, like that list of elements. And again, as we talked about the other day, hydrogen somewhere in the middle there. And again, some metals are more reactive than others. Things higher on the list is more reactive than things lower on the list, and so forth. Ions also react really faster than molecules, because pretty much ions, those positive, negative guys, they're just floating around, ready to go pretty much to react in solutions. So it oftentimes will increase the rates of reaction. Temperature is a big factor as well in terms of affecting the rate of a reaction. Everything's really based on energy and able to interact or break apart bonds or make bonds and those type of things. So, typically when we increase temperature, it typically will increase the rate of the reaction. If you go about 10 degrees Celsius higher, you can usually double sort of the rate of the reaction. Alternative to that, if you throw the thing on ice, for example, typically will slow it down a lot. And as we'll talk about, for a reaction, there is, like, in terms of energy, kind of a hill that, to get to the product, starting with the reactant, there's this hill that, everybody's got to kind of climb. And obviously by increasing the temperature, you're adding more energy, you're allowing more reactants to get up and over the hill to get to the other side, and obviously would increase the rate of the reaction. Vice versa, obviously, as well. If you lower the temperature, you're going to have a less proportion of guys that have enough energy really to sort of get up and over the hill to the other side. And obviously that would result in a much sort of slower reaction taking place. Other things that oftentimes can increase the rate of reaction are catalysts. Catalysts are not reactants, they're not products. So catalysts are not reactants. They're not products. They're not used up in a reaction. They're really just there to sort of facilitate that reaction happening a lot faster. Usually in chemical reactions, we see catalyst written on top of the arrow, like platinum, maybe H plus if it's done in an acid environment. Most of the time we talk about catalysts in the essence of sort of speeding up a reaction. And probably 9 times out of 10, if somebody asks you, what is a catalyst or something like that, they're looking for, that answer of, it will speed up a chemical reaction. But there are actually catalysts that can kind of slow down reactions in certain cases. They're sometimes referred to as negative catalysts. Again, instead of sort of speeding up the reaction, they tend to kind of slow it down. As we'll talk a little bit about towards the end of this chapter, there's different types of catalysts. Some are homogeneous, and kind of like homogeneous mixture means the same throughout. What that essentially means in the case of a catalyst is the catalyst and the reactants and everybody are in the same phase. So maybe they're all aqueous or something like that. Heterogeneous means that basically the catalyst and the reacting guys are really in different phases. So maybe you have a solid catalyst you're using, and maybe the reactants are gases and stuff like that. So that would be more of a heterogeneous type of catalyst. In terms of frequency, in terms of the reactant concentration is really, really important. I mean, when we talk about concentration, we talk about molarity. Oftentimes, again, we think about it as just moles per liter, but we really should remember really what these two numbers or values actually are. It's really moles of solute per liter of solution. And a reminder that the solute is the smaller part of the solution. The solvent is the larger part. And again, both of those guys together is basically what makes a solution. That's that aqueous symbol we typically give. So what part really is there to sort of participate in a reaction? It's actually the moles part. Yeah. So the moles part is really, the part of it that's there that can actually do a reaction and participate in a chemical reaction. So if we obviously have a much larger concentration, in order to get a large M value, you need a bigger number up on top, smaller number on the bottom. And that would mean that we have a lot of moles of solute available. And it's just a process of availability. So if you got a lot of things floating around, there's a pretty good chance they're going to run into each other and start reacting a lot faster than if you had a lower concentration where, it's very sparse in terms of what's floating around and they're available to react. It's going to take longer for them to find each other and really start to react. In terms of gases, the concentration of gas depends on the partial pressure of the gas. The higher the pressure, the higher the concentration. Perhaps you remember our good friend Boyle's law, right? As the pressure goes up, the volume goes down, and vice versa. The pressure goes down, the volume goes up. Well, if we have an increase in pressure, that means that pretty much we have a very small volume, which means all those gas molecules, they're pretty close to each other, which obviously is going to allow them to come in contact with each other faster. And that usually would obviously increase the rate of the reaction. Any question on any of that? We're obviously going to talk about a lot of these sort of factors coming up in this chapter a little bit later on, and we'll talk about some of them in more detail. Any questions on that there? Okay, so I think that's probably a good place to stop here for lectures. So make sure if you didn't do so already that you do put here in the chat box. We have lab at 11:30. Again, a reminder to make sure that you do go through the separate lab meeting that's on the module page there. So don't come back to the same meeting here, come back through the lab meeting. Other than that, if there's no questions, I will see everybody in about 20 minutes or so.